Hello again. In this lesson we're going to be talking about composite functions and their domains. So we learned function notation recently, and we learned how to substitute a value into a function using function notation. Well, what's going to happen when we're looking at composite functions is that we're going to plug an entire other function in, not just a single value. So the definition what we can say about a composite function is when the output of one function becomes the input of another. There's two important notations here. One looks like the word fog. Sometimes you'll hear mathematicians call it like fog of x. I don't know, but it's really read f of g of x. And it might be written like this with this little circle. Or it might be written like this: f open parentheses g open parentheses x, and we're going to close both parentheses. So we would read that either way as f of g of x. F and g are both functions of x. So in f of g of x, we see g of x would be substituted into x in the function f. Similarly, we can do them in the reverse order. We can do g of f of x. In this case, since we see f kind of on the interior here, f of x would be substituted in for x in the g of x function. So let's start looking at some examples to make some more sense out of that. So here we see we're given two functions. F of x equals 2x plus 1, and g of x is equal to the square root of x. So if we're going to find f of g of x, written either way here, that's telling us to take g of x and put it in for x in the f function. So this square root of x is going to replace this x here. And so simply, the 2 stays out front. There used to be an x here. Now it's a square root of x plus 1. So this is the function f of g of x. Now we said we can do them in the reverse order. So let's look at g of f of x or g of f of x. Either way we could write it. Now we've got multiple terms in f of x. This whole group here has to go in to the place where we see x in the g of x function. So the whole group here, 2x plus 1, is going to replace this x here. The important thing here, a lot of students will make the mistake of leaving this x along here. Now this x is gone because it's being replaced with this other function. So here, the square root was still there. That's what we kind of kept from the g of x. But inside here is what used to be just f of x. F of x is on the inside of that square root. So this would be g of f of x. So that's both ways that we could substitute or take the composites of those two functions. Let's look at two new functions. So now we're given f of x is given a whole new function, x squared plus 2, and g of x is the square root of 3 minus x. So if we're going to take f of g of x, we're going to take this whole chunk here with the square root, and we're going to plug it in for this x here that's being squared. Now the interesting thing here is that when we substitute it in, the whole group is getting squared. And nicely, squares and square roots cancel. So the step that's kind of skipped here is that the square and the square root would cancel. We'd have 3 minus x plus 2. So we have a positive 3 and a positive 2, that's 5, and we have a minus x. So the whole expression can be written as 5 minus x. Okay, let's do the reverse. We're going to find g of f of x by taking the whole f of x chunk here and putting it in for where x is inside of the g function. So we take the square root from g and we take the 3 minus. Now here is where it used to be x, but in its place is now the f of x function. So we place x squared plus 2 right in there. Now, we don't have the nice ability to cancel the square and the square root because the whole thing inside here is not squared. We can distribute this negative here, so the line that's not kind of written there would be 3 minus x squared minus 2. So that's how we get just 1 minus x squared by combining the 3 and the negative 2 as our final answer. Now, what we're also going to add to this is thinking about the domain. So we've talked about domain of equations. Well, when we're talking about the domain of a composite function, since the output of the first function then became the input of the second function, what we really need to start thinking about is the domain for both of them. Both domains are going to ultimately kind of become restrictions. So we're going to kind of do this in two steps. The first step is going to be to find the domain of what we call the inside or input function. So whatever, if we're looking at g of f of x here would be the inside or input function. And we're going to find whatever domain there is, if there's any restrictions, we are going to keep them. Then we're going to go ahead and do the process that we just showed up above, where we find the composite function. And then we're going to look at the domain again and see, are there any new restrictions? If there's any new restrictions, we're going to add those restrictions to the restrictions we had from the first step. Sometimes they might overlap, and so we don't necessarily need to kind of list them both or twice, but there might be new restrictions that didn't exist previously. Okay, so here's an example, again, worked out for you. So if you look at, and it's referring to kind of the one we did above here, so if we look at g of x is the square root of 3x, this function has a domain x is less than or equal to 3. So that's going to stick with us. Now if we look at the function f of g of x, well, that's 5 minus x. There's no restrictions on that domain. It's all real numbers. But we must keep the domain of the original, so even though the new composite function looks free of all problems, we're still going to say its domain is this x is less than or equal to 3. So you have to carry along those problems from before. Similarly here, f of x, its domain was all real numbers. You can plug any number in for x and it's going to work out. When we find the composite function, we get this 1 minus x squared inside of the square root. So tricky situation here, but basically only between -1 and 1 are the values that we would be able to plug in here. If you plug in like 2, you're going to get a negative number here. But if you plug in -1 squared is 1, 1 minus 1 is 0, so the square root of 0 will work. We can do that. So this is the domain of the composite function, and so that's going to be our domain overall. We didn't have to add any domain restrictions from the input function f of x, but the output function had its own restrictions. So given two new functions, f of x equals x squared plus 2 and g of x equals 7 minus x. All right, so again, you can see x is less than 7 for our input function, okay? And then when we substitute that in, over here, we get the square root of 7 minus x squared, so that ends up canceling, so we just have 7 minus x plus 2, which turns into 9 minus x. Even though this adds no additional restrictions, we're going to keep our restrictions as x is less than or equal to 7. Okay, I'm going to skip down. I'm not going to do g of f of x here. I'm going to skip down here to this function, example number 4. So a little bit tricky work here. So we've got 1 minus x over 3x is f of x, and 1 over 1 plus 3x is g of x. So when we go ahead to substitute this in, this x here in our f of x function is really these parentheses down here, this whole group here, because that is our g of x function substituted in here. But g of x gets substituted in a second place down here after the 3. This x also gets that substituted in there. I'm going to get rid of that line so it's not over top of what we're going to look at next. So how do we evaluate that? Well, two things I'm going to do. I'm going to go ahead and multiply numerator by numerator. This is really 3 over 1, so that becomes 3 here. Okay? Now, they kind of skip some steps here, so let's take this an extra step here. What do we need to do with the numerator here? Well, the numerator here, notice they have 3x on top. How did they get that? So what they ultimately had to do is they needed to make these two pieces into having a common denominator. So I'm going to, on the numerator here, go 1 minus, and I'm going to just write 1 over 1 plus 3x here. So that's still all over 3 over 1 plus 3x. Okay, great. So over here, though, how do we combine these two together? Well, what I can do, let me change colors here, is to make this the common denominator with the 1 plus 3x, I can multiply it by 1 plus 3x over 1 plus 3x. I multiplied it by 1 ultimately. 1 over 3x over 1 over 3x is still 1. So what we get is we get 1 plus 3x over 1 plus 3x minus 1 over 1 plus 3x, still all over 3 over 1 plus 3x. Well, now in the numerator, I'll change this another color, we have the same denominator. So since we have the same denominator, we can subtract numerators. So the numerators there, I see ultimately a minus 1 with a plus 1. So those are going to cancel out. So I'm left with 3x there over 1 plus 3x. And that's all over 3 over 1 plus 3x. Now that's a mess. But what we really have is fraction division here. So we're going to keep the first fraction, 3x over 1 plus 3x. And we're going to, instead of dividing, this line here is our divide line, we're going to multiply by the reciprocal. So we're going to multiply by 1 plus 3x, the reciprocal here. So this becomes the top over 3. Well, look how nice this is. We've got a 1 plus 3x here and a 1 plus 3x there. They cancel. We also have, you can do this in 2 steps or 1. Let's do it in 2 steps just for a second here. 3x over 3. Well, we've got 3 over 3, so that is just x. Those cancel. We could have canceled it here. 3 goes into 3 once, leaving us just x in our numerator. X over 1 is x. So this whole thing, when we substitute, just turns into x. X has no restrictions, but we're going to keep the fact that the original function, 1 over 1 plus 3x, we couldn't allow negative 1/3 to happen in the denominator. So f of g of x equals simply x, domain, all reals except negative 1/3. Sorry, probably going to need some separate paper to go through these examples on your own. This is probably the hardest part of the lesson. I'm going to skip ahead to something that you'll actually find much easier. So on this page, we're not substituting whole functions in necessarily. What we're doing is we're putting a value into the input function and then taking that value and putting it into the output function. So if we're asked for f of g of negative 3, all we have to do right now is think of g of negative 3 for a second. So I'm going to write f of, now let's go ahead and find the g function. Look, there's 3 functions, f, g, and h. We have to find the right function. And I'm going to basically substitute substitute negative 3. There's a 3 out front, replacing the x in the function with a negative 3. So here is basically this function here substituted in. So that's going to be equal to f of, inside here, negative 9. Well, f of negative 9, I'm going to go to that function, 2 times negative 9 minus 1 equals, 2 times negative 9 is negative 18, minus 1 is negative 19. So I do want you to take the last step to go ahead and write the name of what it was, f of g of negative 3, and say that whole thing is equal to negative 19. So that's what I would like to see the work for that. So we didn't have to go and plug all the x's around. It's not as much algebra, it's more computation here. So again, f of h of 7. So that's going to be f of, h of 7 over here. That's 7 squared plus 1. Okay, so that's f of 7 times 7 is 49, plus 1 is 50. So f of 50. So I go to the f function, 2 times 50 minus 1. And that's going to give us 99. So f of h of 7 is equal to 99. And so for most of these, that's very straightforward. Let's just look at number 7, just because it's a little trickier, but it's really not going to be too terrible. It's just f of x plus 1. It's not one of our other functions necessarily here, but it works very similar as the ones we did on the other side. So what we're going to do is we're going to take the f function, which says 2 times x minus 1, and where we see x, we're going to replace it with what they told us to plug in. That's this whole chunk right here. So this whole chunk is going to replace this x here. Now we still have to carry the minus 1 from the end of the f of x function. Okay, so this is going to tell us we need to distribute. So 2 times x plus 2 minus 1. Oops. Minus 1. So f of x plus 1 is equal to 2x plus just 1 once we combine those like terms. Okay, so now that you've seen those examples, you should be able to try all the rest of the problems on composite functions.